I'm here today to talk about keeping pace with data infrastructure. So I, you know, the data infrastructure space is constantly evolving, and I thought this was important enough of an area to write a little bit of a document on it. And so I put some thoughts here together that I think are impactful. Before I go into that, I want to tell you a little bit about myself and give you some context about why I thought this was an interesting topic of conversation. So I'm Francisco, as previously mentioned. I'm a tech lead manager for data and machine learning at Fast. I've been working in the data science and machine learning space for about 10 plus years, largely at big financial institutions like Goldman Sachs, Commonwealth Bank of Australia, AIG, and some other places. I have graduate degrees in economics and statistics and data science and machine learning from Clemson and Columbia University. I did my undergraduate degree in economics, and what I learned over the course of my career was that I really, really love working with data and working with all the kind of systems in between. And over the last 10 years, it's just completely changed. And in order to continue to stay impactful in the industry, you kind of have to adopt some new technologies. And again, because I kind of got to see that over the years, I thought it would be worthwhile to share some thoughts about it. So there are 4 things that I want to do today. One, I want to talk about incorporating SDLC, a software development lifecycle, into data science. 2, I want to talk about a robust documentation to enable data democratization, and I'll elaborate a little bit more on what that means. And I want to talk third about investing in tools that help you build, ship, and deploy data products faster, because the end result of all of the hard work that we do is some sort of data product, whether that be a dashboard, whether that be a model, whether that be a data pipeline. All of those things are data products that help to enable our business to succeed. And then lastly, of course, I want to leave some time for folks to ask some questions at the end. So in the last 10 years, the way that companies use distributed computing, statistical machine learning, and the software around it has really changed. And so given how much it's changed, how do you keep it pace, right? And if I think back about what data science infrastructure looked like 10 years ago, many of the folks here might be familiar that you'd have some production Oracle table maybe, or some Microsoft SQL server, maybe on-prem, and then you would use some kind of SaaS job to actually extract the data, transform it, and you'd have a bunch of SaaS macros to do all of that, business logic and that cleansing of the data. And then you'd upload it into some table, maybe back into that Oracle or SQL server or some other place. And most of the operations that happened computationally were within SaaS or some other type of infrastructure for compute, the SaaS being the predominant one over the initial years. But then that changed, right? Then things like HDFS and Hadoop came into place. And then we started doing distributed computing, using open source technologies, right? And then Hive became quite popular, and Hive query language kind of became very popular. And then Luigi became an orchestration tool that people would use to actually structure these big data operations as DAGs, directly acyclic graphs. And then it pivoted into Spark, where much of the stuff was the same, except we started doing distributed computing in memory. And so that really sped up how fast we could compute operations and machine learning models, right? And that was really great. And then we're starting to see a pivot towards, just cloud native distributed computing on platforms like Snowflake or Rockset and all these other tools that are essentially handling much of that complexity for you. But then there's also all that middle layer of business logic, data transformation that still exists, right? And then now we're at this stage, like I just mentioned, where all of this has changed in such dramatic ways. And some businesses still are running the old technologies from 10 years ago, because obviously migrations are super costly, and they're hard because there's a lot of business logic you have to kind of reinvent or revert, especially if they're core to your business. It doesn't always make sense to do that quickly. So these were kind of the big topics that I had in mind when writing this presentation. And I feel lucky that I've gotten to see, since I started my career kind of early at that churning point, how much of this stuff has evolved. And so even anecdotally for Fast, in 2 years, we have, 500,000 lines of code, 75 plus engineers, and over 25 data pipelines. And that's only just from sources, right? If I told you how many actual operations and executions we have, this would be much bigger. And this is not to just over-index on fast, but to talk about, well, we're really only a year and a half company, right? And we've seen this already. We have terabytes of data that we're starting to ingest, and the scale at which we're doing this data operations is just blowing up faster and faster. And so it is, at the micro level for us, crazy to see how this is already changing and how we're pivoting to evolve with the needs of our organization. But, obviously for the existing large institutions, super critical for them too. And so on the first topic, incorporating an SDLC into data science. Define your North Star. I think, always start with first principles, right? And to us and to me, that means that you want to thoughtfully engineer the tools, processes, and architecture to build, ship, and deploy data products faster, right? And I think I'm particularly passionate about this because I find this just fun. The data space is so interesting to get to understand, model human behavior. It's just such an exciting space, right? We've seen data science just explode and enrich product experiences all over the internet, and that's such a great space to be in. And so, in our world, in our lens, we really think about making sure our North Star is that we build tools that enable people, that enable an architecture to be kind of holistic, thoughtful, comprehensive, documentable, readable, and intuitive. And then ultimately to help us just really have an outsized impact as a team. So we do that by starting with the end game, right? And by that, I mean, define what the end result of whatever it is you're building looks like. If it's a model, where is that model result, that prediction, that score going to be used, right? Don't worry about the particulars of the table, the data structure, but find out where it's going to be used. And then work your way backwards, right? Don't start with the model and then try to figure out after the fact. Start with the end and then work your way backwards. It's a small thing, but what I learned over my career is that oftentimes that isn't where we start. Sometimes we want to just build a model to see if it's effective and then figure it out. And that can be impactful, but typically what I found to really be able to hit the ground running fast is start with that end game, that end result. Where is this model or data pipeline or tool going to be used? And how do I make sure that I'm set up for success to deliver it there? And then treat your model development as code. As a once data scientist and then ultimately engineer, I think oftentimes you see a lot of model development, right? Whether you're doing a whole bunch of really rich feature engineering or experimentation, that you don't see it as code. But code is code, right? And we don't want to over scrutinize it and slow things down, but we want to make sure that we treat the model development thoughtfully and seriously, so that way it can be reproducible, it can be easy to read, easy to distribute, and share it across the team, right? If the way we look at this internally is that if we're working on stuff so important, we want to make sure that other people can work with it, use it, and enhance it. And so treating the model development process as code too is very critical to that, right? Thinking about testing, thinking about the subtle things like naming conventions and readability. All those things ultimately impact how you can distribute and share and empower others with your code. And it's important to realize that your models are versioned artifacts, right? I think oftentimes people historically looked at models as saying like, oh, well, this is model v1, we can just move away from it. It's not code. But a model, no matter how big it is ultimately a static equation, right? Or at least one version of a model. And so when you think about that artifact, you can have that as, some sort of, like explicit artifact in an S3 bucket. You could have it as an explicit, commit into your code. And obviously that gets challenging as certain models, like especially large scale neural networks, get quite big and bulky. They do cost quite a bit in storage. But really, when you start to think about your models as effectively an API, some of that starts to change, right? Because a model at execution time is effectively an API. And when you think about it that way, you'll be a lot more diligent about making sure that you're set up for success to manage what the complexities downstream implies. Because, machine learning systems, as they scale, get increasingly complex and hard to understand the downstream complications. But when you treat it as code, that starts to turn a little bit differently. So all models degrade, monitor them. This is mostly true, not uniformly true. What I say is that in the private sector, when we're not working on computer vision or natural language processing, we find that time really dictates the decay of a model, right? I'm sure most folks that have worked on building models have observed this in their development, that models do have a half-life, and you have to make sure that you're set up to monitor that up front, especially if it's in a production system, right? And especially if it's facing users. We know that the model will degrade and it won't be as effective, and so we want to think up front, like, how do we make sure to update that model and manage the deployment of a new model and still have that replayability of the old model, right? So that we have this kind of version control over these models. Because again, once people start using the score and then other people start using reporting, there are all these downstream effects that you just don't always have visibility into. And so it's an important thing to keep in mind. So the next thing I want to talk about is robust documentation. This is something I'm exceptionally passionate about. As an IC, as someone working in data, as someone who loves data, this is a subtle thing, but so powerful and such an important concept, especially at large institutions I've worked at, that sometimes this can really be a bottleneck in the work that you're doing. And so some principles that I think about is transparency. Transparency is so important, and that's not necessarily in the data, because obviously privacy is something that you want to manage thoroughly, and security is something you always want to be conscious of. But transparency into how data is operated on, how data is being ingested, really, really enables teams and teams of teams to be impactful with data. They can actually just go in there. I recall many times as a younger person working in the space, I would look at one table and I would find some strange idiosyncrasy in it and try to reach out to somebody from that was the owner of it, right? But turns out they just created a report on it, and it turns out they created a report on someone else's report, and so on. Ultimately, to when I would find the source of truth, which is someone in a different country, in a different time zone, and I didn't know who the owner of that was, and maybe they had left, right? And so understanding the full lineage of that data is so critical to just be able to resolve data issues, because data issues happen, right? That's just natural, right? Humans are fallible. No engineering system is completely bulletproof. We have high quality engineering, best talent, and things just naturally happen, right? At every organization I've worked at, I've had miscellaneous data discrepancies, and they are always resolved. But in that point in time, there will be some idiosyncrasy in the data, and you have to document it. You have to handle some edge case for it to transform it, so that when you're doing your analytics, your reporting, it doesn't throw off those things. And so having transparency into the system really helps with that. And so a couple of points I want to make before I go into that. Tables should be structured for the intended purpose, right? So there's a lot of NoSQL just new types of databases that we're thinking about. The old version was very structured databases. In real-time systems, that makes sense in online systems. But then for offline analytics stuff, you want to make sure that you structure whatever table or view that you're making for the intended purpose. And why is that? Because that allows you to actually give an explicit business user some structure and easy, intuitive product effectively to work with. And another key point is in documentation, you want to make it self-service because again, and the example I gave is kind of more junior analyst looking through all sorts of documentation, trying to find the rabbit hole of data that I needed for my problem at whatever point in time I had. If you make it self-service, you empower other people to really just be effective in their work. Because if you're the point of failure in some work stream, someone has to come to you and ask you a million questions about the data, you're slowing them down, right? And that's so consequential at scale. And so that's something that we definitely value and think about, right? And then again, just democratizing that information really helps reduce this kind of common theme I observed in my career, which was that there's a data person that you just have to reach out. I remember several different colleagues of mine who always mentioned, oh, you just have to find that data person, wherever they are. And in some cases, I flew to different countries, like Australia, to just find that data person. And when you did, it was really high impact. But from an organizational perspective and a team perspective, that's a single point of failure. And that's a bad process, right? And so you have to think about how you better manage that. And so how do you keep a system transparent and prevent these kind of data silos, right? Don't get distracted by local optimization. And so what does that actually mean, right? Someone's creating some pipeline, they create this really, really long SQL file with all sorts of transformations pulling from a bunch of different source tables because it's just easier to work with and navigate. That works on some one-offs, and when you're being hacky or agile, and that's just what you want to do, that's fine. But at scale, again, that's going to be very consequential. And so we really, really want to think about how that cascades. And from a software development perspective, that's code, right? And if you have multiple of these brittle pipelines of code, it can be very consequential, right? In the sense that like everyone's doing the same thing. And, you know, if someone has an if statement in their logic when not the other, and those reports ultimately roll up to the same thing, it can completely throw off the numbers, right? And so it's brittle in that sense. And then having all these parallel, pieces of code, maybe doing similar things, that doesn't support really good documentation. And so it's really like opaque onto what's actually the business meaning of this, right? Because ultimately, SQL and data transformations represent business logic, things that are really core and valuable to the organization that you want to reflect, right? Whether it's like a simple case one saying, oh, for this little set of cases, remove the dollar amount because that day it was thrown off for whatever reason, right? And that, because again, that ultimately rolls up to your reporting, how you do your financials, how you define your products and experiences. So it's really important, even though it's kind of a subtle thing. And so how do we handle this, right? That's the exciting part. We use open source tools like dbt. And so then I want to talk about a little bit about the tools themselves, dbt being one primary example, to help you build, ship, and deploy these data products faster. And so again, what you want to do is invest in tooling that makes you move fast. And so see, these are some of the tools that we use, at Fast that we find impactful for our organization. That won't be true necessarily at every organization, but it is true for us. DBT being a really great way to host a bunch of great documentation, do data engineering transformations, and then also structure DAGs in a really rich way. And what that means is that, again, as these SQL tables and transformations get really big and intricate and a bunch of business logic embedded, you can document them and structure them as directed acyclic graphs, DAGs, things that you would used to use things like Airflow for. And kind of some of the challenges that came up with Airflow is that you'd have a bunch of different Python jobs, right? All of which their own kind of custom pieces of SQL. And then you don't know exactly what's going on in there. You can see the DAG and the scripts ad hoc, but you won't have the visibility and connection, the references to actually be able to say, oh, these two pieces, these two independent DAGs are actually doing a similar operation, pulling from the same table. Why don't we collapse those, right? DBT helps us, and then again, treating this kind of process as software development helps us really be impactful and thoughtful about managing that. Some of these other analytics platforms like Snowflake and GitHub really help us manage this diligently as well. Again, we get to be really impactful in this space. And so, I have some closing thoughts I want to share with everybody. Code is code always, like I mentioned. That was a phrase that I learned earlier in my career, and it's one that is increasingly thoughtful. That's not to say that you should treat every piece of code with the same level of rigor, right? You just want to make sure that you're thoughtful that this code that I'm operating on impacts stakeholders, like business stakeholders, our users, and we want to make sure that we have good hygiene with it, right? And the right process and the right infrastructure around it to support that. You want to make sure that you value documentation a lot, but at the same time, I promise you, no Excel file will ever be good enough. Any documentation is a lost cause if it's not coupled with code. I've seen so many Excel files representing, some data dictionary in my career, and oftentimes what they end up being is outdated, stale, and distracting, and that can be actually more harmful than helpful for some of the work that we're doing. And so it's really important to understand that and be thoughtful about that, because it's a non-trivial decision, right? So coupling your documentation with code is extraordinarily important, and being very rigorous in your reviews of code, whether that's through pull requests or whatever process you use internally, is really important, right? You want to make thoughtful architectural decisions. Software and hardware for data and machine learning has evolved quite significantly. And one point that I only briefly showed as a bullet point in the previous slide is that we decouple our compute infrastructure from our software development, right, and our data infrastructure, because the how we store data, how we process and analyze data has evolved very differently than how we actually compute on data over time, right? Over the years, that's going to continue to evolve, and people have made extraordinary milestones in this space. So it really is important to separate this compute side from this, like how you do the compute, right? Because like those are constantly evolving, right? 10 years ago, we didn't really care about GPUs. Now we care a lot about them, and who knows what the next 10 years will hold. And then again, lastly, and probably most importantly, is solve problems with the intent of empowering self-service knowledge. When it comes to data and how things evolve over the last 10 years, is data has only become increasingly important. We see this at FAST. We see this at every organization, in the Valley and elsewhere, that data is how we are operating within the new digital era. And so if whatever it is that you're solving for isn't traversable, isn't understandable to lay people, it's going to be a real big struggle, and it might not scale for you in the way that you want. And so really focusing on solving that problem with that, hey, this is important enough that someone else is going to look at it. How do I make sure I allow them to look at it? Is really valuable. So now that is it. And now I'll allow us time for some Q&A. And so thank you all very much. I really appreciate your time. I know you could listen to a bunch of other folks speak, and so I appreciate you taking the time to listen to me.